Hello and welcome. My name is Manuel Navarro, and I'm going to present our paper entitled Meta-Learning for Fast Model Recommendation in Unsupervised Multivariate Time Series Anomaly Detection, a work done alongside my colleagues at Huet, Alexis and Dario. As the title indicates, the context of this paper is anomaly detection algorithm recommendation, meaning being able to choose which algorithm to use on a new dataset in order to detect anomalies present on it in the best way possible. This paper is further contextualized in the industrial setting that we found ourselves when working on this problem, namely, one in which we cannot assume that the data we'll see in the future is similar to the data that we have seen in the past. Recommendations need to be issued quickly, and data is shaped as multivariate time series. To tackle these conditions, we present three different contributions. To address data variety, we propose a two-headed meta-recommender called authors. To make sure our recommendations are fast, we designed two new recommenders, and to ensure that we were representing our data accurately, we employed time series meta features, a concept that which we'll define in the next slide. Regarding the state of the art, we first note that we restrict ourselves to recommenders based on the extraction of meta features, meaning information that can be extracted from the data without labels, and from those meta features build a mapping to the algorithm's performance. Having said that, there are three main recent works that fit this criteria: MetaOD, Elect, and Lotus. And while we won't go into the details of the differences for this video, the two lacking areas we identified with them were a focus on time series and the importance of novel patterns versus known data. With this in mind, we turn to authors, our meta recommender. To clarify the process of this kind of recommenders, they have two phases: an offline training one and an online application one in which the recommendation is issued. During the offline training, all the possible algorithmic configurations we want to be able to recommend are tested on a bunch of training data, and in parallel, meta features of these training datasets are extracted. Lastly, with these two matrices, a function that predicts algorithmic performance from the meta features is fit. During online recommendation, once a new dataset arrives, its meta features are calculated, from which a performance estimation of all the possible configurations is extracted, and then issuing a recommendation is just a matter of choosing the algorithm with the maximum estimated performance. Having said this, this is authors' diagram. As we see, it has three components, and we're going to go over each of them individually. The first building block of authors is its novelty detection module. When a new dataset arrives, its meta features are extracted, and they are projected together with the original dataset's meta features using UMAP, and then clustered. The label for the new dataset is extracted, and if it hasn't been assigned to any cluster, or it is assigned to an excessively small one, authors decides it doesn't have enough previous data to extract fine-grained patterns and passes it to our recommender for novel data, uregression. If, on the other hand, the dataset is assigned to a big enough cluster, it is passed to our known data recommender, CFACT. Let's now go over these two. Uregression is the first recommender we will explain, and it is designed for novel data. It is based on approximating the performance matrix using singular value decomposition, and then creating as many random forests as singular vectors are kept from the decomposition to predict U from the meta features. During recommendation, an estimation of the performance is rebuilt by estimating U and then multiplying it with the other components of the SVD. In order to use this recommender for novel data, we use few singular vectors to force it to only learn broad patterns that we expect to be generalizable across datasets. If our new dataset is similar to existing ones, we can exploit this similarity to create a better recommender. We do so by first clustering different algorithmic configurations in the performance matrix and separating them based on their performance profile across datasets. Then we build as many uregression recommenders as clusters we have found, with a higher value of singular vectors for their internal SVD. This process of clustering allows us to reconstruct the performance estimation with a higher accuracy. Lastly, we turn to the meta features set that we propose to use with authors. Previous works have used generic outlier detection meta features that would not take into account the temporal behavior of the anomalies present in our setting. To solve this, we propose to use time series meta features, specifically Catch-22, a standard set proposed in literature, which we turn into multivariate by extracting first the 22 univariate features per time series in our data, and then aggregating them as the minimum, 3 quartiles, and the maximum. This forms a vector of 110 meta features in total. We now turn to experiments, and we first remark that our objective was to compare authors against state-of-the-art methods in the task of anomaly detection model recommendation. We compare it against MetaOD and 3 baseline methods: global best, meaning just taking the model that worked best on average across all data in training; nearest neighbor, which recommends the algorithm that worked best for the closest dataset in the meta feature space to the new one; and regression, which builds a random forest per configuration to recommend. To evaluate them, we created a performance matrix with batch and streaming algorithms for a total of 507 configurations, and we ranked them using the area under the precision recall curve, presented as the percentile of the distribution of areas for a single dataset. Thus, it will always be a number between 1 and 100. Lastly, regarding data, we used 94 datasets from 4 different public sources, and we created 2 different scenarios with them. Scenario 1, a 10-fold stratified cross-validation, in which all data sources are present in all folds, and Scenario 2, a leave one source out scheme, in which each fold contains only 3 sources. We also repeated all of our experiments with 5 random seeds. So the first experiment we did was the main result of the paper, which is a direct comparison of the average performance obtained by each recommender, estimated across the 5 random seeds we tested. We can see how for Scenario 1, regression and global best are close to authors, which is still superior to them, but for Scenario 2, authors manages to lose only 2.5 points in performance, whereas the rest decrease significantly. This shows that, across scenarios, authors not only improves both the state-of-the-art and the baselines in recommendation performance, but also maintains a very good performance in scenarios in which the data is completely novel. Now we're going to show 2 ablation studies. The first one is a study of the effect on performance of the number of singular vectors kept in the singular value decomposition of U-regression, which affects authors in the performance of both heads. We can see how there's only a variation between using 2 vectors or more, with more vectors being better for Scenario 1, but worse for Scenario 2, whereas using only 2 vectors helps keeping the performance consistent across scenarios. This validates our hypothesis and justifies using a different number of singular vectors for the 2 heads of authors. The second ablation study that we did was comparing authors against its building blocks. In this plot, we show the average rank obtained by each recommender when pitting them against each other, and we see that authors seems to exploit both methods accurately, obtaining practically the same average rank and average performances as the best performing recommender for each case. This confirms that the novelty detection mechanism of authors is working as expected. Lastly, we want to show a comparison of using Catch-22 as meta features instead of using the meta features proposed in MetaOD. The table shows the percentage of dataset across recommenders where they can be considered to be equal, or where Catch-22 or MetaOD's meta features are better. We observe that across recommenders they are mostly equal, with a slight edge for Catch-22, which validates our hypothesis that they would be a valid meta feature set. To conclude this video, we have presented authors, a 2-headed meta recommender for anomaly detection, capable of employing novelty detection to decide which recommender to apply to new datasets. We have also presented 2 novel recommenders, U-regression for new data and CFACT for known data, and testing them on 94 datasets across 4 different sources, we've shown how authors can consistently choose algorithms in the top 10% for known data and top 13% for novel data. We refer you to the full paper presented at the AUTOML conference for expanded details and experiments, and the release open source code and experiments, which you can find on the link on the QR code on the slide. Thank you very much for your attention.